All right, welcome back. We are ready to move on and continue with Chapter 2 in Campbell's Biology. This time around, we are going to be talking about Concept 2.3. The formation and function of molecules depends on chemical bonding between atoms. Now, again, new word here, molecule. What is that? I briefly touched on the concept of chemical bonding, but now we're going to take a much deeper dive into it. Okay? So, if you remember from concept 2.2, where we were talking about the idea that atoms with incomplete valence shells want to have complete valence shells. And I touched on the idea that if you only have one in your outer shell and you can get rid of it, your next shell down will be full. Or if you have four in your outer shell and you can find four more to share with another molecule, you can again have a complete outer valence shell. Or maybe you can gain one if you're only missing one. Having that full outer shell is much more stable. And having that full shell being stable is why that whole row of elements, called the noble elements, which have a complete outer valence shell, is chemically inert. They can't react with anything because they are as stable as they can possibly be. Okay? So, there are two ways that atoms can achieve this full outer shell when they don't start off with it. Okay? One way is they can share electrons. The other way is they can transfer electrons. So either give up one or gain one, or maybe two, depending. Okay? Now, these interactions where you are either sharing or transferring electrons usually results in those two atoms staying close together. And this property of holding them together is something that we call a chemical bond. Okay? Now, there are two types of chemical bonds. One is a covalent bond, and the other is an ionic bond. Okay? And these are what we call the two strong bonds. So let's dive in first into what covalent bonds are. Okay? So covalent bond is when sharing a pair of is the sharing of a pair of valence electrons by two atoms. Okay, so in this covalent bond, each atom considers the shared electrons to be their own. Okay, so in this case, both atoms who are sharing this electron gain a benefit. Okay. So let's start off looking at something very simple. So we'll start off with the most simple element, hydrogen, which has one proton, one electron. Okay, this is the 1s orbital, and it can only hold two electrons. Okay, so if each of them just needs one way of accomplishing this is for them to share both the electrons. Okay? So as these individual atoms become close together, what's going to happen is the electron cloud of this atom is going to be drawn towards the nucleus of this atom, and vice versa. So this electron cloud is going to be pulled towards the positive character of this atom's nucleus. As they come closer and closer together, they finally achieve a point where those electrons are kind of orbiting both. Okay, not kind of orbiting, they are orbiting both. They are in a shared space. Okay, and typically that space is somewhere in between the two nuclei. Okay, there is a little bit of flexibility there, but typically it's a shared space. Now, once we do this, recognize that this atom, or this nucleus, is considering both electrons, its original own, and the other one to be its own, and vice versa. This links these two atoms together, and it forms something very stable. Okay, we call this stable thing a molecule. Okay, so a molecule consists of two or more atoms held together by covalent bonds. And again, these covalent bonds are very strong. These covalent bonds can come in many different flavors. Two atoms might be able to share a single electron each, or they're sharing one pair of electrons. This is considered a single bond. But you can also share two pairs of electrons, which is called a double bond. You can share three pairs of electrons. This is called a triple bond. Okay? There is no quadruple bond because the geometry in order to achieve that isn't possible. Okay? And we'll briefly touch on that later, but I wouldn't worry too much about it. Okay? So we have this word molecule, which is talking about two or more atoms being held together by covalent bonds. Okay? Now, if you recall, previously we used a similar type of term called compound. And a compound is a substance consisting of two or more elements in a fixed ratio. Are these the same thing? Not necessarily. Okay? You can have molecules that could also be considered a compound. But you can also have compounds that are most definitely not a molecule, and you can have molecules that are most definitely not a compound. Okay, and we'll kind of dive into this a little bit more. Keep in mind, one of the key things here is that a molecule, it requires covalent bonds. A compound requires two or more elements. Okay? So let's go back and look again at that hydrogen-hydrogen covalent bond. And there's a couple ways that we can represent this bond. One is something, a notation that we call a structural formula, where we have the symbol for that element, H, linked to another H with a line. That line is representing two electrons that are being shared in a covalent bond. Okay? This is, if you have a very complex molecule, it's a very good way of representing it because you can see how different things are connected together. A more compact way of describing it is with this, what we call molecular formula. Here, we just simply call this molecule H2, and we recognize that that is a single unit. And again, molecules largely act as a single unit. Okay? Now, coming back to this differentiation between molecules and compounds, notice that this is a molecule because it has a covalent bond, but it is not a compound. A compound requires two or more elements. Okay, and we only have a single element. There are two of them, but they're not different. Okay, so in this case, our hydrogen molecule is a molecule, but it is not a compound. Okay, here's a lot of different ways of representing it. Here is an electron distribution diagram where we can show the electron shells, and we can see that both of these electrons are being shared by both shells that are now overlapping. Here's other ways of showing it. We've represented this here, the structural formula, where we have the two electrons being shared represented as a line. If there was a double bond, there would be two lines, and I'll show you an example of that. Here we have the Lewis dot structure, where we just show the two electrons in between, as dots in between the two H's. Now, none of these really represent what this molecule would actually look like, this is what that molecule would actually look like. Okay, so it's two spheres that kind of have become severely overlapped. This is what it looks like in three-dimensional space. All right, let's go on and look at a double bond. Here we have oxygen. Oxygen has 1, 2, 3, 4, 5, 6 in its outer valence shell, so it needs 2 more. This oxygen is in the same scenario. It needs 2 more. Well, fortunately, the geometry exists that they can share both of them simultaneously, as you can see represented here with those electrons being in both shells. Here we represent that in the Lewis dot structure by having the symbol, and we also show that there are lone electron pairs that sit out here. Okay, those lone electron pairs can be important to how a molecule behaves when interacting with other molecules. So we show that here. Okay, this is a much more simplistic view of it, where we replace those shared electrons with single lines, and we get rid of the lone pair electrons. This is a very simple representation. We can implicitly imply that those electrons are there. Again, it's not what it actually looks like. It looks something more like this. Okay? Again, this is a molecule, but not a compound, because both members are the same element. Okay? Now, here we have water. Again, oxygen needs 2, hydrogen needs 1. So another way of accomplishing getting everyone full is for one oxygen to share electrons with 2 hydrogen atoms. Okay? So you can see here that these electrons are in energy shell 2 of the oxygen, but in energy shell 1 of the hydrogen. And you can see that's the same is true here. Here's the Lewis dot structure, here's the structural formula, and this is what it actually looks like in three-dimensional space. Okay? Of course, it doesn't have color. The colors are just shown in to help us distinguish which part is what element. All right, now, in this case, this is both a molecule and a compound. Okay? Because there are 2 or more elements. There's oxygen and hydrogen. And this is occurring in a fixed ratio. You always have 2 hydrogens for every 1 oxygen. Okay, so both a compound and a molecule. All right, here we have something called methane. Carbon needs to share 4 electrons. Hydrogen needs to share 1 electron. So here we have carbon sharing electrons with 4 different atoms of hydrogen. Okay? And here's the Lewis dot structure, the structural formula representation. And in three-dimensional space, this is what it would look like. Okay? Something to notice here is when we represent it here, it looks like it's all 4 of the hydrogens are sticking out kind of around the circumference. That's not how it actually looks. Here, each of the hydrogens takes up a position that is as far away from the other hydrogens as possible. Recognize that these hydrogens have a positive charge in their nucleus, and they are going to be repelling the other hydrogens. So they're going to move into a position where they are as far apart as possible. So covalent bonds can form between atoms of the same element or atoms of different elements. Okay? Again, compound is a combination of 2 or more elements, so things can be both a compound and a molecule, or things can be a molecule and not a compound, or they can be both. Okay? The amount of bonds that can form is referred to as the atom's valence. Okay? And we will pick back up on this in part 2 of this video.